Welcome to the oil refinery, where safety and operational efficiency are the top priorities. Since its installation at the refinery, the COMPACS system has continuously monitored the health of coke drums and other static equipment. Its role is not only to prevent sudden failures, but also to optimize maintenance, ensuring the safety and efficiency of the operations. Prior to implementing the COMPACS system, the coke drums at the oil refinery experienced significant issues, such as fires caused by ruptures in the drum walls. These tears were primarily due to thermal stress, fast linear expansions, and abrupt mechanical stretching, which were difficult to detect and alleviate without monitoring the drum's technical state. The only solution at the time was to increase the frequency of inspections. However, these inspections are labor and time-consuming and do not guarantee the detection of all potential failures. This reactive approach often led to unplanned shutdowns and safety hazards, underscoring the urgent need for more reliable and efficient problem-solving. The COMPACS system has three crucial components. The first is the hardware infrastructure, which processes signals most cost-effectively. The second is the physics-based AI, which identifies the cracks and leakages in static equipment at their emergence with an accuracy of more than 97%. The third is an easy-to-use software platform that instantly informs personnel with precise prescriptions on what should be done to prevent degradation and failure, and how much time they have to take action. Each coke drum at the refinery is equipped with multiple sensors that provide accurate real-time data. These include acoustic emission sensors, pressure sensors, fiber optic local strain sensors, and benchmarks for monitoring the drum's inclinations during operation, all together forming a robust network that leaves no room for uncertainty. Implementing the monitoring system on coke drums presented significant challenges due to the high temperatures and harsh environmental conditions within the coking process. The system had to be designed to withstand extreme heat while filtering out external noise, such as rain or hail, and internal noise caused by the ongoing processes inside the drum. This required advanced sensor technology and sophisticated algorithms to ensure accurate data collection, filtration, and analysis. Acoustic emission sensors detect early signs of fatigue and damage while the drums operate, allowing for timely maintenance. Three benchmarks monitor inclinations of the coke drum during operation. Local deformation sensors offer detailed insights into the drum's deformation, helping predict and prevent failures. In June, the COMPACS system detected an anomaly in the inner cladding layer of the coke drum. Deformation, caused by thermal stress, pressure fluctuations, and mechanical wear, had begun to affect the drum's structural integrity. The increased energy of the acoustic emission signal was located in the AE25 sector. At the same time, the COMPACS system issued the prescription, catastrophic acoustic emission, energy class 4, lower mode, inspect. Here are temperature and linear strain trends, and their gradients characterize the drum's operating conditions. Although the temperature and linear expansion didn't exceed the thresholds, the COMPACS system identified that the gradients did for every coking cycle. Fast temperature and expansion growth appear during the start of pressure testing 1, coking 2, and coke water cooling 3. This leads to the nucleation and development of fatigue cracks in the drum's material. The gradients of local deformation allow for the evaluation of the stress-strained state of the coke drum metal body. To ensure safe operations and increase the drum's residual lifespan, the growth speed of the temperature and linear expansion should be reduced. Acoustic emission signal parameters monitoring provides control of units' operational processes. After installing the COMPACS system, it became clear that each shift conducts the operational process differently. This difference does not influence the produced goods, but it reduces the residual lifespan of the machinery. Analyzing the data provided by the COMPACS system, the reliability team figured out that the increased gradients of linear expansion was caused by cooling the coke drum with cold water. To prevent a repeat of the accident and increase the lifespan of the coke drum, the cooling process was divided into 3 stages. Initially, cooling by steam, then cooling with hot water, and finally cooling with cold water. Before any action was taken, the energy of the acoustic emission signal exceeded 2.7 millivolts squared. After the cooling procedure was changed, it didn't exceed 1.3 millivolts squared. Here are the trends for acoustic emission pulse energy and accumulated energy. The top graph shows the acoustic emission during the coking process in the coke drum. Each peak on the graph corresponds to a coking cycle, where spikes in acoustic activity are observed, indicating changes within the drum. Since June 2018, the amplitude of these peaks has grown over time. It exceeded thresholds with several exceptionally high values in August, suggesting intense processes or possible damage. The bottom graph displays the accumulated acoustic emission energy over the same period. Initially, the level of accumulated emission grows slowly, but the more acoustic emission energy exceeds thresholds, the sharper the increase of the accumulated energy. This sharp rise towards the end of the observation period indicates significant changes within the drum, as has been known later, related to the detachment of the inner cladding layer. The coke drum was shut down for planned maintenance, and the maintenance team revealed an inner cladding layer detachment of approximately 3 square meters at a very particular sector, which the COMPACS system pointed out on the 2D digital twins map. Thanks to the COMPACS system, timely inspection and maintenance was fulfilled, preventing significant consequences such as fire or explosion. When the system detected significant deformation in the higher part of a coke drum, it provided real-time alerts and clear maintenance prescriptions to the personnel. By acting on these alerts, the personnel could perform condition-based maintenance, preventing severe damage and costly downtime. Thanks to the COMPACS system, the refinery has significantly reduced maintenance costs, prevented accidents, and improved operational efficiency. According to published reports, our customers' total savings exceeded $1.7 million in 2014 alone. The COMPACS system's physics-based AI analyzes the sensor data, identifying potential failures with high accuracy. This predictive capability is crucial for maintaining operational safety and efficiency.